Thank you for the invitation. It allowed me to get my thoughts together on this topic. We've been working on bits and parts of it, and this was an opportunity to put an entire talk together. You will notice that I have far more slides than I can cover in 30 minutes. The idea was to have an internally coherent presentation, but I don't intend to cover all of it. You can use the slides for later on as background, and I hope you won't mind me skipping through a bunch of slides or going fast on some parts. The idea is to give you an overview of how distributed RDF and SPARQL execution, what works have been done. So I should say that all of my work in this area is done jointly with two colleagues, Lei Zhou at Peking, Peng Peng at Hunan, and Lei Chen at Hong Kong USD. And these are either my former students or my academic grandsons. My work with my own students focus on property graphs, mostly the last few years on streaming property graphs, but that's a talk for another day. So the RDF use cases are quite common. You've probably focused on all of these, and RDF is one of the building blocks of knowledge graphs and the semantic web, and the linked open data in the latest count is about 1,200 data sets, and nobody really exactly knows how many triples there are. But the best guess I could find is over 100 billion triples. My guess is that that's conservative, because UniProt on its own, which is the biological the knowledge graph in itself, or RDF store in itself, reports over 84 billion triples. But the RDF data sets are growing, and the growth in this case is fairly fast. LOD's growth from about 10 years ago to today has been substantial, and all of these lead to the issues of managing this RDF data. So for people like me who are fundamentally data management researchers, when you give us a data model and a query language, we are in our zone. I think this is where the data management issues come up. We could look at declarative query processing, and the obvious solutions are not efficient. So the database community or data management community typically focuses on efficiency in query execution. The initial systems for RDF were single machine or centralized, but with the growth in data set sizes, we've gone to distributed solutions, what I call scale out, which is on the left, which is really you have a large RDF data set, and to get better performance, you typically partition this data set over multiple machines, and then look at executing SPARQL queries in parallel. And on the other hand, the independent data sets have been growing with a lot of RDF data sets, and these have their own owners, and they have their SPARQL endpoints, and and they do want to keep and maintain their own data. And for that type of an environment, federated solutions have been developed. So that's the setting for the distributed SPARQL or distributed RDF. There was at the recent EDBT conference in about 2 weeks ago, Katja Holze gave a very nice keynote on knowledge graphs, and the way that she categorized the systems is depicted here. And she basically talked about centralized and then client server and so on to streaming. I I worked on this a little bit more, and I think I like a little bit finer granularity. So from my perspective, there is the centralized, and centralized ones can be either more or less relational. So take the triple table and work with that, or they could be graph-based. I'm not going to be talking about that. Or they could be scale-out solutions which have a number of different alternatives, or they could be federated solutions where you have SPARQL endpoints from which where you can actually execute SPARQL queries, or some of the endpoints may not be SPARQL endpoints. They can store RDF data, but have no processing capability. And streaming systems have started to appear as well in terms of the RDF streaming. So what I'm going to do today is only talk about part of the scale out, the query partitioning cloud-based partial evaluation, and the federated systems. The others I will not touch upon. Katya's keynote is going to be put, I think, on YouTube. I don't think it is there yet, but if you check EDBT 2021 conference website, you will probably find when that goes online. I would highly recommend watching her presentation. So the outline of the slides, not the talk necessarily, is it starts with an RDF introduction, which I won't go through because I understand you've covered the basics of RDF. I have 2 points there that I want to touch upon that are important for the later discussion. Then I have some overview slides on centralized systems. Again, I won't touch upon those, and then I'll jump into scale-out systems. So these are mostly for background. The only thing I want to touch upon in RDF introduction is the semantics of SPARQL. And I'm only focusing on a subset of SPARQL, which is called the BGP, Basic Graph Pattern. So a SPARQL query, as I'm sure you looked at, consists of these triple patterns, and a collection of these query that consists of only these triple patterns, nothing else, no unions, no optionals, etc., is called the BGP, basic graph pattern SPARQL query. So if you really look at those, the SPARQL semantics is one of subgraph matching using homomorphism. And the operational semantics, how you can actually think of this, is that you go into your triple store, you find all the triples that match each of these individual triples. So on the right, this one has 5 triples, triple patterns, and on the right I have 5 lists as tables. And really the one way to think about SPARQL semantics is that you're taking joins. So because the subjects have the same variables. Sorry, I wrote this wrong. This should be subject joins. You're doing a subject join, and then you're doing a subject object join, and then here you're doing a subject object join as well. These all should be different. So that's fundamentally the only thing that you need, that is important to keep in mind. The other thing about SPARQL is the SPARQL query shapes, because these come quite a bit in the subsequent discussion. These SPARQL query shapes play a role. Most of SPARQL queries are of the star shape, where you have a single vertex from which these predicate or property edges emanate. You can have trees, chains, cycles, and more complex queries, which might typically people, when they talk about these complex queries, they talk about 2-star queries or 3-star queries attached to each other, but they don't have to be only stars. They could be anything. So this one is a star, a chain, and a cycle query. Okay, so this is the only part of SPARQL that is important to follow. So now I'm going to just jump into scale-out systems, and I'm going to talk a little bit about graph partitioning, because all of these systems assume that the graph is partitioned, and then I'll talk about three different approaches. So the objective of partitioning, of course, and this appears in relational systems, etc., as well, is that you take your data and you somehow partition it, or sharding is what it's called. Partitioning in this case is horizontal partitioning. So you take the table and horizontally cut it and put each partition in a different worker, and then the query then executes in parallel on this one. And some of the systems that have proposed taking the triple table and simply using hashing, simple hashing on the triple table to get the partition. One of the problems with this is that when you're doing those subject-object joins, etc., you get way too many intermediate results, so your join costs increase. And in particular, when you're doing inter-partition joins, these you need to move data around, and this becomes difficult. So the issue here is the triple table does not capture the relationships between the triples. So people have actually started looking at direct graph partitioning techniques, where the data is not simply a table, but it's a graph, but you have the same objective where you want to partition it into different worker nodes or machines. Two typical ways, approaches to this, and this is not specific to RDF, this is for property graphs as well, is either edge cut, or what we call vertex disjoint, or vertex cut, or edge disjoint. And the objectives in the graph partitioning is in any data partitioning is you want to keep the partitions to be more or less balanced, so that the workload is balanced across the worker nodes. You want, and depending on whether you're doing vertex disjoint or edge disjoint, you want to put one vertex or one edge, each vertex or each edge in a different partition. And while you're doing it, you want to minimize the edge and vertex cuts, because those are the things that either cause extra communication or state maintenance, as I will show you. Most of these techniques, graph partitioning techniques, are what I call workload agnostic. There are some techniques that take the workload into account. What if my workload consisted of this? What can I do with the graph? But the techniques I'm going to talk about are workload agnostic. So vertex disjoint partitioning puts each vertex in one partition. So this will cause edges to be cut. And we want to minimize those, because each edge cut causes communication across different partitions, different worker nodes. The alternatives are hashing on the IDs of the vertices, the simple case, which gives you very balanced, and it's very fast and simple, but it causes high number of intermediate results and high number of edge cuts. And the gold standard in this in this domain is what is called the Metis family of algorithms, which basically goes by taking the graph and kind of coarsening the graph, so where you're looking at subgraphs that you represent as super vertices, and then you successively do these until you get to a graph you start from G0, you get to successively coarsen graphs to Gn, where Gn is so small, it doesn't matter the cost of partitioning. You use any partitioning technique to partition Gn, and then you start uncoarsening, going back and reflecting that partition on the full graph. That's the idea. So a very simple case where I took one graph and I used a hash function based on the vertex labels, and you get this, and all of these dashed lines are cuts, and that's actually painful. This doesn't reflect it well, and the vertex disjoint partitioning performs well for graphs with where the degrees are low, but on power law graphs, which are very common, they cause many edge cuts, and you can use METIS, but the METIS has very high computation overhead, and it really doesn't scale to large graphs. So almost all of the systems that provide do vertex-based partitioning, they provide hashing as part of their toolbox to go. And the important issue here is that we, in this case, as I'll talk a little bit later, in RDF case, what becomes more important for minimizing interpartition joins is not to minimize the edge cuts, but really to minimize the predicate cuts. And I'll demonstrate that a little later on. So I'll skip this because I haven't gone over the example, but the example is in the earlier part. In the edge disjoint partitioning case, we put each edge at a different partition, and what this causes is that the vertices are replicated. In other words, if the two edges that are placed on different partitions share a vertex, that vertex has to be repeated in both places, and that means that if the state of those vertices need to be maintained in both places. So if there are that becomes an issue. In RDF, this is less of an issue, simply because the RDF is a simple graph model where the vertices only have labels, so there isn't much issue of updating on those edges. And edge disjoint partitioning is used a lot in cloud-based systems. I'll talk about later on, because in cloud-based systems, what they do is they look at each edge with the particular predicate, and all the edges with the same predicate go into one file that goes on HDFS. And the objective in cloud-based systems is to minimize the scans, so that this allows you to focus the scans on a particular file, depending on what the SPARQL query is asking. So that's important. And again, if I take this and do it there, do the edge disjoint partitioning, I get what is on the right, and these dashed vertices are replicated vertices between different partitions. So number 2, the home partition is P2, but I replicate it in P3 as well. Okay, and these perform well on power law graphs, and they are fast and highly serializable. But the star queries are problematic, because in star queries, what you want is the vertex and all of the edges coming, all of the neighboring vertices to be in one partition, and edges will break those up, and we might get high vertex replication. So again, the example there is so. Let me jump into the 3 types of scale-out systems I'm going to talk about. The first one is query partitioning systems. So these start with a partition data set. So D1 to D6 are the partitions. We've already partitioned the RDF graph. Now we partition the SPARQL query. So we get subqueries, and the idea is that we wanted to partition the SPARQL query in such a manner that I can execute as many of them. I can execute each of these as independently as I can, or on one of the worker nodes. So I try to avoid the joins that of the partial results that are created by these subqueries. So the problem is really distributed execution of these queries over the partition data. And this is really very, very analogous to distributed query processing and optimization in relational systems. And there are a number of systems of this type. The main idea of these systems that you need to keep in mind is how do I partition the data and the query in such a way that the interpartition joins are minimized. And all of the techniques that that have been proposed, there's a high degree of coupling between query decomposition and the partitioning that they use. So they either say, this is the partitioning that we do on the data, and here's how you can partition the query based on that partitioning, or they say, this is how I want to partition the query, this is the characteristics that I want, and to meet those characteristics, this is how I partition the data. So two example systems that I'll talk about. Again, this is a partitioned graph where into two partitions. The amber ones are one partition, blue ones are the other, and these green dashed edges are your edge cuts. That's basically where communication between partitions goes. One system says, let's first do a partitioning using metis, but they admit that they can actually use something else that doesn't matter. This is the base partitioning that gives you a nice one. And then I'm going to replicate vertices using n hops. So if I'm using one hop, then for in the amber one, I'm going to reach out into the blue and pick the one hop reachable vertices and replicate them in the amber one. Similarly, for the blue one, I'll reach out and replicate the other ones. But it could be n hop, and of course, as n gets higher, your replication cost increases. But you can evaluate more queries independently in that case. But in the extreme, of course, it's you don't partition it, but that's not what you want, of course. So when you get a query Q, what you look is the radius, which is really what is the distance from the query at the center that matches the center of this graph to the edge. And if the radius of the query is larger than n, then I have to partition it into several subqueries such that the radius of each subquery is less than or equal to n, and then I execute each of those subqueries on a partition. The second alternative is very similar, which is vertex block proposal, and they were proposed 2 years apart, interestingly. They also talk about partitioning the triples across vertices, but they use what they call semantic hashing. So what they do is they first form triple groups. They say they group the triples based on whether they have the same subject, or whether they have the same object, or whether they have the same predicate. So they can have S triple groups, O triple groups, or P triple groups. And then they use a hashing function to allocate each of these triple groups into machines. And then they basically do allow replication. The idea of replication is this. So if this is your baseline partitioning, and you have this query which reaches there, this query is not independently executable, of course, because you need to take the join of the partial results over these three partitions. But the idea they have is that if I extend P1 by a little bit over, then I can handle P1 on its own. And similarly, I can extend P5 a bit, and I can handle P5 on its own. The proposal is not very, very different than the other one. It's just how they partition the query and how they partition the graph slightly changed, but the main idea is the same. We've been working on this, and this is a little bit different. This is not published yet. It's under submission. The main point of our work was the recognition that all of the previous work tried to minimize the edge cuts, but the edge cuts are not what really causes the interpartition joins. If you can increase your edge cuts, but if all of the edges that you cut involve a single predicate, they're all born born on, or they are all resident or something, then really the class of queries that you can execute independently increases quite a bit. So the idea here then is that we want to instead of minimizing edge cuts, we want to minimize the predicate cuts even at the cost of increasing edge cuts. So the next couple of slides introduce how we do it. I'm not going to go through. It's the similar idea to METIS, which is that we coarsen and then we partition. But coarsening, the really important case is being able to choose the internal predicate. So how do I form the super vertices as I coarsen? And that we use a greedy algorithm that's based on weakly connected components. And we choose those the predicates, and then we partition the coarse graph on the right, and then we go back and uncoarsen the original graph. And we have a formula for we have a methodology for processing queries on it, and it gives us fairly good performance. I don't have time to go through it. So the query partitioning approaches are really quite high performance, great for parallelizing centralized RDF data, but the query decomposition is not easy, and query decomposition is difficult even in relational cases, but they're difficult here as well. And as I said at the beginning, the query decomposition and data decomposition are very tightly integrated. It would be interesting to adopt a relational distributed query processing methodology here. By that I mean that what we do in the relational case is that we do query decomposition, we do data localization. The query decomposition gives us an algebraic query. We look at how the data is allocated, and then we take this algebraic query tree and partition it so that the joins are minimized, and then we create a distributed query plan and optimize it, figure out how to do how to put together the results. And when we execute the query on these local sites, then we execute the distributed execution plan. This is really not done in the case of the query partitioning based graph processing, unfortunately, because there isn't much work in this domain. Fundamentally, as I'll mention later on, there isn't a well-developed algebra for SPARQL. One alternative is partial query evaluation. We did this a little bit. So again, the RDF data is partitioned. We don't care how it's partitioned, but we don't partition the query. What we use is the partial query evaluation technique that programming language people have invented. So what that is that when you have a function on X, we rewrite the function as with two arguments. One is S, which is the sum of the arguments that you know, the inputs that you know, and the other one is the unknown inputs. And then we basically execute the f prime on S, on just S, to get the what is known, and we leave the D as the unknown, and we execute another function on it to get the final answer. So in our context, what are the known inputs? S, it is basically the query itself, and what we also know is all of these partitions plus the what we call the extended edges, which are really extended vertices, which are really vertices on the other partition that are at the end of crossing edges. And then from here, the idea is that we send the query to each partition. Each partition computes partial results, but these are not final results, because what we have are, we're missing these crossing matches. and then we assemble it, the final result from these partial results by a join operator. And the setup is what you would expect. A bunch of machines over which data is distributed. We do local evaluation on these machines, and then we do an assembly phase, which can be either centralized, we send the results back to where the query originated from and assemble there, or we do distributed joint processing.
So, Tamer, we've got about 5 minutes left.
Okay, I'll finish. So this has high performance due to parallelization. It doesn't have the problem to deal with the query decomposition, but you need to modify the RDF systems at each site to be able to deal with this partial query evaluation technique. The final category here is cloud-based solutions. So again, the data is, RDF data is partitioned, and the SPARQL query is run as MapReduce jobs. This is really your typical data parallel execution. And the main idea here is that query operations are MapReduce jobs. And so you need to have a MapReduce systems that implements all of the relational operators that you might be using in this processing. And as I said, you typically do edge-based partitioning here to get across. An example is Hadoop RDF, where they split the predicates, and then they basically split each predicate. So each of these is a file. So all the triples, which has the has name predicate, are in one file, and so on. And then they do further dividing based on the object part of the graph. And then when they get a query, they first choose a particular file, and for each triple pattern, and they execute that triple pattern on those files as MapReduce jobs, and then they do a MapReduce join at the very end. So I'm going very short here because there's a very nice book that you can probably, Stanford has a subscription to this, so you can download and read it. These are highly scalable systems. Again, they're inherently fault tolerant because of MapReduce, but the performance is bounded by what MapReduce can do. All those intermediate relations that you generate is going to be causing a lot, and you have to write the results of those to HDFS and then run the join job as a separate MapReduce job, which means you have to read from HDFS again, and whatever optimizations you do, you have to do it outside of the MapReduce platform. Let me talk about federated systems. These are different. As I said, you have these RDF sources. So what you really, when in the scale-out systems, we took a D and we partitioned it into a set. Here we're going the other way. We have a set of D sub i's, and we're putting them together to get a D. And each of these D sub i's are a SPARQL endpoint, meaning that if you give them a SPARQL query, they can execute it. And you get the SPARQL query, you decompose it, you run it in each of these SPARQL endpoints, and then you compose them. And typically, you have this RDF resources, and the main idea is one of data integration. You're starting from bottom, and which are the sources, and you're going up, and you always have a control site which maintains a bunch of metadata that is about access patterns, et cetera. And typically what you do is you do the query site, the control site takes the query, does a query decomposition, and selects which parts of the query or which QI should be executed on which of the sources. You do a local evaluation on the sources, you get the results back, and then you join the partial results at the other end. The typical way that you can do query decomposition, I'll demonstrate by an example here. You have this query. We basically determine, this can actually, you can tell from here as well, the prefix is G. These two triple patterns can be executed on geonames. The third triple pattern can be executed on any one of these on any one of these. So we'll have to choose. And the third, the last one can be executed at New York Times. So you divide these into 3 queries, Q1, Q2, Q3, and you execute them at those sites and then combine the results. And then you do some data localization, as I talked about. And therefore, what you basically happens is exactly what I described. You take this, you determine the sites where you're going to execute it, you execute them, and you compose them. That's the federated. The question is, what if you have some which are not SPARQL endpoints, in which case you use the mediators, and you build mediators that pretend, that have wrappers that pretend that these sources can execute SPARQL queries. So they act as if there are SPARQL endpoints there. And there are examples of federation. Uniprot is one. This is an example that actually goes to multiple Uniprot data stores and gets the results. It's a service-oriented federated query execution. And the advantage is that this is data integration approach. So you take the data sets as they're given. You're not trying to do anything with them, and you go from there. But the SPARQL endpoints are notoriously unreliable. There are studies that show that at any one given time, up to 64% of these SPARQL endpoints are offline. So if you pose a query, they may be offline. So basically what you need to do is this kind of fault tolerant or query processing techniques that can withstand those the offline ones. And not all RDFs, when you do have to do mediators, that's heavy duty. So the conclusion is that there's a lot of work. I listed the systems at the beginning, but I cannot say that the technology is as mature as distributed relational data management. They're not. Part of the reason is that there are multiple communities that work with RDF. Semantic web community really focuses on functionality, much less on performance. So if they can execute queries, generally they're satisfied. And we worry about performance, but the data management community has focused more on property graphs than on RDF graphs, and that's an issue. And most work considers only BGP, but full SPARQL 1.1 has these optionals and unions and aggregation and so on. Those are really not well handled yet. We have some work that's ongoing. Algebra definitions are starting. There is a recent paper that's defining an algebra for SPARQL that I'm not sure how I feel about it yet, because I'm in the middle of studying it. But there is a prospect that if those algebras are successful, we could get somewhere. And there are a lot of opportunities for using views and view-based optimization, multi-query optimization, cost-based optimization. These are open problems that we haven't done. And the work so far only considers static RDF graphs. And as they evolve over time, how do you do incremental query processing to cope with this is not known. So I'll stop there.
Very good.
It took a few more minutes, but I apologize.